Hi everyone, and welcome to Erik's Electronics Workbench, and part 2 of the Simpson 260 Series 6 Volt-Ohm-Milliammeter repair. Now, if you haven't seen part 1, you'll definitely want to check out that video. It'll bring you up to speed on the troubleshooting and testing that I did on this meter to get to the point that we're at now. So I'll post a link to part 1 in the description. So, new parts have arrived. It's time to continue on with the repair. So all of the resistors right here have come in. New 9-volt battery snap, and this front bezel with new glass. So the reason that I picked up this new bezel with the glass is because, if I zoom in a little bit closer here, grab this piece right here, you can see on this front panel, this was really common on these meters, see how the front has this number that's been scratched in or sort of etched in right there? And it's really common to put identification numbers and things like that on these meters over the years. So it'd be nice to clean up the meter and not have that on the front panel. So this is very easy to change. There's just a couple screws you can see right there, and then there and right there. So you take those off, this front will come right off. And then when you put the new piece on right here, let me just set this over here again. You have to be careful, this zero adjustment right here, there's a little pin, and you want to make sure that that pin lines up correctly. And also, the glass that's in here, you have to coat this with an anti-static coating. If you don't do that, then a static charge can build up on this and it will affect the needle movement, and basically the needle in the meter movement will repel with the static charge that's on this glass. And you don't want that to happen, it'll affect the accuracy. So you have to just wipe this down with an anti-static cleaner. You can actually use a dryer sheet, something like that, or an electronics cleaner that's safe for plastics and things like that. That's a lot of times sold as like a dust-off type, dust repellent type cleaner. So I'll do that before I install that piece. So let me just grab this piece here. And I had already mentioned that I noticed on the part 1 video right here, get that touched up again, you can see that wire was smashed down right there. Almost cut completely through, so I picked up the new 9-volt battery snap. And on this 9-volt snap, you want the type where the wire comes out like the T-shape, the wire exits between the two contacts. You don't want the wire exiting out on the end, it won't fit correctly, or if it does fit, it's kind of a snug fit. It's meant to come out on the center point. So that's, again, this design right here. And these are nice long wire leads on here as well, so they can reach all the way down on the board. You can see the length of that wire right there. So it should work out. Now on this board, if I turn this over here, you can see these resistors on here, and I'm going to show you this drawing, which is touched up there. And again, in part 1, I went through and did the troubleshooting and measuring on these resistors and the areas that were definitely troublesome. You can see this is melted right there, clearly a problem. Other resistors weren't measuring at all. This is basically open over here. Some are out of, or many of them are out of tolerance and out of spec. So set that down here and get this drawing right here. So this is out of a service manual. Get this so you can see the whole thing here. And after I went through all of the resistors, the obvious ones where they've been overheated and damaged, of course, need to be replaced. But I took a measurement on every resistor in here, and they're all supposed to be 1% tolerance. But I found that many of these resistors that looked okay, especially down through here, the multiplier resistors, they were actually out of tolerance, so they had drifted beyond the 1%. And the idea with this meter is to make the meter as accurate as possible and something that I can use on the bench for troubleshooting. And I'd like to have the meter work the best that it possibly can. So basically, if they weren't damaged and overheated or physically didn't look correct or had been replaced with the wrong kind, if they otherwise looked okay, they had drifted. So almost every resistor in this meter needs to be replaced, and that's why there's so many resistors you can see over here. All of these, they all came from Mouser Electronics, so they're all very high quality, Dale and Vishay and so forth. Now, this meter uses a lot of odds, well, I shouldn't say a lot, but quite a few unusual values of resistors. So there's 1 megohm and things like that are typical values, but there are some values in here that are they're oddball, that you just can't find them. So some compromises had to be made. And I'll show you some things that I'm going to do, the values that I picked out and why I think they'll work okay. So let me pick a couple of those resistors. I'm going to hook them up on the ohm meter. We'll see what the actual value is on the new resistor. We'll look at what the old value should have been, and I'll show you how the numbers work out. So here's an example of one of the resistors that has a non-standard value. So this is R12. If we look at this page right here, you can see R12 is located right there on the board. So it's used as a current shunt. And the original resistor's value was 0.468 ohms, or 468 milliohms. So unless you have a parts meter to pull the resistor out of, you're not going to find a 468 milliohm resistor at vendors like Mauser and DigiKey. It's just a non-standard value. And if they do list it, it's going to have large minimum orders. It'd be basically a custom production part. But a standard value, the next closest value, is 0.47 ohm, or 470 milliohms. So that's exactly what I purchased. So if we look at this label right here, you can see. So it's a 2 watt, 0.47 ohm, 1%. And that's the resistor that you see connected right there. And on the meter, it says null on the display right there, because the meter has been nulled out before I connected the resistor to offset the resistance that's in the test leads, because this is such a low value resistor that the resistance that's also in these test leads would skew or cause a inaccurate reading. So the reading that we're seeing here is exactly the value of this resistor. So it's very close to the promised value of 0.47 ohms, and again, it's a 1% tolerance. So how do these numbers actually work out? Well, the original resistor, 0.468 ohms, or 468 milliohms, at 1% tolerance, that means that as a high value, it could drift as high as 0.47268, and as a low value, it could drift down to 0.46332. Now, the new resistor at 0.47 ohms, also 1%, it could drift as high as 0.4747, or perhaps as low as 0.4653. So you can see the value that we're measuring right here is certainly within the promised value. It's within the 1%, but it's also within the range of that original resistor, 0.468 ohms, very, very close to that value as it sits there, just a few milliohms off. But it's also within the tolerance of that original resistor. So I believe this resistor will work perfectly fine in the circuit. Now this is a 2 watt resistor. The original resistor's wattage, I'm not exactly sure what it was rated at, but if you take a look at 0.468 ohms, the most current that would flow through this resistor in this circuit is 500 milliamps. That's the highest current that will go through this resistor. So 500 milliamps through a 0.468 ohm resistor, which again is very close to the value we're seeing here, is only 117 milliwatts. So 117 milliwatts, or 0.117 watt, is way below the 2 watt rating on this resistor. So this resistor isn't going to even get warm. And again, its value shouldn't be drifting at all because it's not even going to warm up in the circuit. Another resistor with a non-standard value is R16. Now it's supposed to be 11.2 ohms. And if we look at this drawing, here you can see the location of R16 right there. So even though R16 looks like a large power resistor, it's really just the old style way of making a precision wire wound resistor. So R16 is used in the ohm meter circuit, and under worst case conditions, it would never see any dissipation over 200 milliwatts, and in normal use, much, much less than that. So I'm going to replace R16 with 2 resistors in parallel, which will be these 2 resistors right here. So the replacements are 22.5 ohm resistors, and 22.5 ohms paralleled together gives 11.25 ohms. So take a look right here, you can see the specs on the new resistors are right here. So again, 22.5 ohms, 1% tolerance, and they're rated at 1 watt each. So the wattage rating is well above what the circuit is going to require, so they won't be warming up at all, and certainly won't be drifting. So again, these 2 in parallel, you can see the reading that we're getting up here, very close to what we'd expect at 11.25 ohms, actually 11.2933. And I've nulled out the lead resistance again, so it says null right there on the display. Now again, the original resistor was rated at 11.2 ohms, 1% tolerance. So that means the original resistor could have drifted up as high as 11.312 ohms, or perhaps down as low as 11.088 ohms. So this value that we're seeing right here is well within the tolerance of what that original resistor would have been in. So I think paralleling these 2 together will work perfectly fine. R17 is another resistor with a non-standard value. So the original resistor was 1.109 k ohms, or 1,109 ohms, with a 1% tolerance. But I'm going to replace it with this 1.1 k ohm resistor, and you can see the measured value right there. And again, this is a 1% tolerance resistor, and you can see the specs on the packaging right here. So 1.1 k ohm, 1%, quarter watt. So going back to the original value, 1.109 k ohms at 1% means that that original resistor could have drifted as high as 1,120.09 ohms or as low as 1,097.91 ohms. So our 1.1 k ohm value is right in the middle, shouldn't be any problem whatsoever. Now there are two other resistors in the meter that are also non-standard values, and then all the other resistors are standard and easily found. But R18 and R20 were the two remaining resistors that aren't easily found. And R18 is supposed to be 123.57 ohms, so not a standard value at all, but I was able to find a 124 ohm resistor, and the 124 ohm resistor is rated at just 0.1%, 15 ppm, so very precision resistor, should work very well. That's less than a half an ohm difference from that original resistor, and again, the original resistor was a 1% tolerance, so we're well within that spec. And then R20 is supposed to be 113.77 k ohm, and I was able to find 113.86 k ohm, and I'm actually surprised. 113.86 k ohm doesn't sound like a standard value, but Mouser had quite a few in stock. You can also find 113 k ohm, but 113.86 got us a little bit closer, and it's also rated at a 1% tolerance, so should work perfectly fine. All right, so all the components that needed attention have now been replaced. So you can see the pile of old parts, and taking a look at the board right here. So these three resistors, and then skip the next resistor. There's another resistor then hidden under this wire, so those four, and then this resistor right on the corner. Those are all original, but all the other resistors were replaced. The potentiometers all tested out okay, so I didn't have to replace any of those. I replaced both of these germanium diodes, and I'll talk a little bit more about those in just a moment. And then looking at the back side of the board, the new 9-volt battery snap. And then I took some time and just cleaned up all the flux that was on the board, not only from the work that I did, but some previous repairs and work that were done. There was a lot of flux that had built up right in this corner right here and other places as well. But in this corner, I know that these two resistors were replaced with the wrong type. And it looked like maybe someone had done the work without removing this board. Maybe was trying to reach underneath the board to do the soldering. The solder was pretty heavy over here, and just a huge amount of flux that had built up on the board. So I cleaned up all of that, and it turned out very nice. And luckily for the age of this board, none of the traces lifted when I was desoldering components and doing the work. And I was worried that maybe in this corner here where previous work had been done, if this excessive heat was used, it could damage the traces, and then you come in and remove those components and then the trace just lifts up. But luckily nothing like that happened. Everything is in good condition. So again, for the age of the board, it's kind of surprising. I have worked on these Simpson 260 meters that were older than this. So this is Series 6, and some of the earlier versions, the traces are very delicate on the boards, and you can be as cautious as you want, use as least amount of heat as possible, and still the traces will tend to lift on the boards. So, but anyway, the board turned out very nice. Happy how it looks. Now taking a look at this section right here, this piece. So this resistor is original, it tested perfectly fine. The current shunt for 10 amp measurement right here, this stiff piece of wire that runs across here, has a very specific resistance, and we'll take a closer look at that in just a moment as well, but it tests perfectly fine. This original resistor right there is testing okay, but this resistor right here was replaced, so that's a 7.5 meg ohm resistor. The original one was out of spec. And this capacitor tests perfectly fine as well. So you can see it's a Sprague, and then 0.1 microfarad, 400 volt DC rating. And these are known as a Black Beauty capacitor, but when they have this red writing, you kind of see the marking on there. Typically the red writing type is a difilm capacitor, and the difilm capacitors hold up very well over the years, and they don't become electrically leaky. So if you come across these types of capacitors that may look similar to this, And there are the old style paper and foil type capacitors, sometimes also the very old type that were the wax type capacitors, with basically they have a wax coating on the outside of the capacitor. Those become very electrically leaky and have to be replaced. They're basically turning into resistors, but again, these difilm type capacitors hold up very well over the years. The old saying is that if it's red, go ahead, so typically the red marking on those, you are good to go. So I'll show you this on the capacitor tester, and you can see how it's testing. So, also, this capacitor, the purpose of it in the meter is for measurements where you have a DC voltage with an AC voltage writing on the DC, and you want to block the DC voltage. So if you look at the front panel, this attaches to the two terminals. One terminal is marked as output, and then it goes over here to the positive input. So it's just bridged across those terminals. And so if you connect to the output terminal right here, then your signal goes through this capacitor, and any DC voltage is blocked and AC voltage passes through. The reason that this says output is because it's intended to connect to maybe an instrument or an amplifier where you're measuring the output signal, and you would have that DC voltage with an AC voltage. So this output doesn't mean that there's a signal coming out of this terminal. Again, this is an input for what you're measuring. So we'll get back to the capacitor tester, and I'll show you that in just a moment, how this is testing. But taking a look at the two diodes again right here. So these two diodes are part of the AC voltage measurement circuit, and they have to be the germanium type diode, and they should be reasonably closely matched for the circuit to work correctly. Now, these are the two originals right here. And you can see these were taken out of the circuit. I don't know if they're original to the meter or not. They do look like the original type where they have the two little black bands on the end. Get that a little bit closer here. So you can see there's two separate black bands and then the clear glass type. So again, those do look original, but they've been cut out of the circuit and then resoldered. Basically, there's a little bit of the lead that was going through the board and then the solder that was done there. So something was going on. They were either tested or maybe replaced. Something happened in that circuit. So I thought, well, those should be replaced just so that I know that they're the right type and that they're going to work okay. So yeah, go back over here, this tester. So I'm using the 1N100A, that's the replacement type. And right here I have a little pack of them there. So I just went through all of these diodes and I found the two that were closest match, which actually measured both identical, so they're a very close match. I'll show you an example here on the tester. So there's a couple different part numbers that can be used for replacement diodes, and I think some of the later Simpson 260 meters from the factory might use the 1N100A, but again, the 1N100A makes a very good replacement, so you can use that in any of these Simpson 260 meters. So here's one of the diodes right here. So this particular type has the blue color to it rather than the clear glass. Get this to touch up a little closer here. Oh, the part number will show up. These do have a part number on them, the other type does not. So get this connected here to the meter. So turn it on there. So what I did is I went through all the diodes that were in that little package, and I just wrote down the measurement values that the meter was showing, and then I just went through and compared and picked the two that were the closest, which they actually had exactly the same measurements on both of them, so they're a very close match. Now I know this says a Zener diode tester, but this does test regular diodes as well, but it is also meant for Zener diodes. You can test LEDs and other devices too. So it starts with the 2 milliamps, so that's the current through the diode right now, and this, where it says VZ for voltage of the Zener, this is actually in a just regular diode like this, because this is not a Zener diode. This is just the forward voltage drop at this current. And then you can see right now the slope resistance. It says 25 ohms. So what this meter is actually doing is the current that you have right here, this is the middle current for the measurement on the slope resistance, and then it's measuring and figuring this value with a current that's a little bit higher than this value and also a little bit lower. So you have 3 points, and then it's coming up with this value based on those measurements. Oops, it turns off on its own. Okay, so going back here, if we go to 5 milliamps, you can see the values change a little bit. 10 milliamps of current, values change again. Have to settle in just a little bit. This is actually taking an update about every 2 seconds. So if things change just a little bit, it will update. It's not just a one-time measurement. And 15 milliamps. So you can see the slope resistance value changes quite a bit. Forward voltage drop changes as well. Go back to 2 milliamps, it just cycles around again. So with those measurements, again, I just wrote that down for each of the diodes and the two that were the closest match. Picked those out, and that's what I installed on that board. So that should work very well. And again, if these aren't closely matched, it can affect the accuracy of the meter in the AC voltage measurement. So let me move things around just a little bit here. I'm going to turn that off there, and then bring this over here. So earlier in the video, I was measuring some very low value resistors, and I was using the null feature on the meter and just the traditional 2-wire measurement. And with the null feature, then you can null out the resistance in the test leads, and then the value that you get is what's actually in the resistor. But another technique that you can use is to do the 4-wire resistance measurement. So this is in the 4-wire setting right now. And these Kelvin clips right here, you can see there's 2 wires that go into each clip, and then the 4 wires over here going into the meter. So without nulling anything at this point, you can see this very low value that's being displayed, essentially sitting very close to 0. And you can still null this out if you need to, but this is much closer to 0 than if we had the other way where you end up getting the lead resistance as well. So by using the 4-wire resistance mode and then these clips that are designed for the 4-wire measurement, then you're able to get down to a very, very low value. So you can see here, this is ohms and then milliohms and then hundreds of micro-ohms. And it is sensitive how things move around just a little bit as well. You can see just moving the leads, how things do change just a little bit. And then if you don't have, exactly a good connection right there, it can cause things to change. It is very sensitive to the measurements. So yeah, you can see right there, it's basically sitting exactly at 0. And again, that's without nulling anything. So let's take a look at the 10 amp current shut, which is this stiff piece of wire that goes through here. It has a very specific resistance. It's supposed to be 0.025 ohms, okay, very low value. And a traditional ohm meter isn't going to be able to measure this. It's going to look basically just like, a short touching together, but there is a very specific resistance on that wire. So with the 4-wire mode like this, it makes measuring a shunt resistance like this very, very easy. So let me just clip these over here. Now the tricky part is getting the good connection on these clips right onto the terminals, because there's a little bit of flux that's on there. You want to make sure that you have a good connection. So let's make sure that that settles in there. It takes just a little bit of time. See, it's not quite getting the connection right there. Let me just make sure that's... Okay, there you go. So again, very close. So that's supposed to be ideally 0.025, and we're at 0.026, and some change. And if I changed the power line cycles, it wasn't 10 power line cycles. Now that's 100 power line cycles. So the readings slow down, but they'll stabilize a little bit more. And you can see it's very close to what it should be. So again, 0.025 ohms or 25 milliohms, and we're getting 26.3 milliohms. So it looks like this shunt is in good condition, no problems with that. But I just wanted to show you an alternate way to measure very low values of resistance. All right, let's check that capacitor using the Sencore LC102. So pardon the camera movement, but I'm just going to go down to the workbench. You can see the test lead from the LC102. It's all the way down. And there's the capacitor right there. So I've already set up the LC102 so that it knows what the expected capacitance value should be. and also the voltage, so 400 volts, that's the maximum rated voltage of that capacitor, and it'll apply 400 volts when I do the leakage test. So we'll start with that. So press this, and it will start to measure the current flow through the capacitor. So it starts a higher value as the capacitor is charging, and it starts to fall, which is normal. So 0.15 microamps. It says 0.12 microamps in bad, but now it goes to good, so it may have been taking just a little longer to charge than it was expecting. The value is down to a very low value, 0.04 microamps, 0.02, now down to unmeasurable, 0 microamps. So no problems there, that looks perfectly fine. So again, a capacitor that becomes excessively leaky, that value for the current flow through the capacitor would remain very high. So this falls all the way down to 0 microamps, is essentially not measurable, any current flow through the capacitor. So looks perfectly fine. And then the capacitor value measures as 0.1252. 54. So no problems there. If I go over here, I enter it as a 0.1 microfarad, so it knows what to expect. So the capacitor is working perfectly fine, no issues. We can certainly leave it in the circuit. All right, so I had the new bezel with glass installed. I'm really happy how it turned out. The meter looks like brand new. So I spent some time cleaning the dial face with just a delicate cotton swab, and there was a number of spots that were, just some dirt that had accumulated over the years, and a little bit of dust and things like that. So just very carefully went through and removed those spots. And again, the dial looks, like factory new. So it turned out really nice. And I have this zero adjustment set, so the needle is resting right on the 0 point. So the next thing I want to do is check the movement of this meter, and to do that, I'm going to move the camera up here, so pardon the camera movement. So for this test, and also for the DC calibration, I'm going to be using this Keithley 236. So I'll talk a little bit about this in just a moment. So the first thing that I want to do is check this meter movement, and on the back of the meter, right here, the two terminals right here and right here. So those go directly into the meter movement. And with this check and this test, you have to be very, very careful, because this meter has a full scale deflection all the way over to the right-hand side of about 50 microamps. But it's a little bit less than 50 microamps when the needle is pointing all the way to the end of the actual dial. And we want to see exactly what that is. It's not really needed for the actual calibration, but I'm just curious to see what the measurement is. And it should be about 48 microamps, maybe just a little bit under that, but probably around that amount. And I just want to make sure that that's actually how this meter is behaving and actually working. Okay, so again, 50 microamps is full scale off the end, but a little bit less than that is what we expect to see for the dial itself. Now again, the microamp range that this has, and there's no protection, you have to be very careful. You would never want to hook a battery or something like that to power this meter. That would completely destroy the movement in the meter. You have to use a source like I'm using here with this Keithley 236, or a power supply that has a similar capability that can control down to the microamp range. So right now this is set to 10 microamps, so it's in constant current mode. You can see right now it's sourcing current, measuring voltage. So it's also in the compliance mode, and that's really important because this can output up to 110 volts DC. And in the compliance mode, it's set to a maximum output of just 100 millivolts right now. So what that means is that even though this is trying to do a constant current of 10 microamps, the ends of the test leads are not connected right now. And if I connect them like this, then you can see the voltage essentially falls to 0. Okay, so now 10 microamps is flowing through the wires in the test leads, but the voltage is essentially 0 because there's no resistance. But if I open this up, now the voltage across these test leads is right just shy of 100 millivolts, 0.09985. So that's again the compliance voltage. and it's trying to do 10 microamps, but no current is actually flowing. All right, so this is the set value, this is the measured value over here. All right, so I'm going to connect this right here to the meter, and I have to do this test before the main circuit board is installed, because once the main board is installed, you don't have access to these meter terminals without other circuitry that would be interfering in here. Okay, so this is the only time you can get directly onto the meter with no other circuitry in here. Okay, so I'm just going to set this out of the way for a moment, but again, this is how it's connected. Positive on this side, negative here. Polarity marks are up on the top right there. You can see, I think, the glare off of there, but anyway, there's polarity markings on in the casting right in there. So with that connected, turn this over here. You can see right now 10 microamps, and now we have a little bit of voltage as well, okay, about 20 millivolts. And you can see it does have some deflection on the meter as well. So what I'm going to do is just hold this here very carefully, like this. And actually, I think what I'll do is just move this over here. So this digit is flashing, so that's going to change when I turn this knob right here to make the adjustments. As I start to increase that, you can see how the dial is indicating higher. So I'll just back that down. So we're about halfway right now, and you can see 25 microamps. Again, 50 microamps full scale, so that makes sense. That would be about halfway at this point. So it's looking good. So I'll just keep turning this up here. It's going all the way over. You can see the voltage is rising up a little bit higher. So right there, go down, and let's move this over to a little bit finer resolution. So to my eye, it looks like that's right on the last tick mark on the dial. Okay. So it looks like 46.5 microamps. So that makes sense. That's just a little bit less than the 50 microamps full scale deflection. So if I go all the way over, just turn this down, 46, 47, 48, 49, and 50. So you can see what happens, 50 microamps, it does in fact go off the end of the scale. So perfect, the meter is working the way that it's supposed to at this point. That's very good to see. So I'm going to install the main circuit board, and then we'll continue on with the DC calibration. And for the DC calibration, I'll continue to use this Keithley 236, and I'll get everything set up and I'll show you how to do that calibration. So some of you might be asking, how do I know that the Keithley 236 is supplying the current that's indicated right here when this is an entered value for the current? This is not an actual measured value on this display, where this is a measured value for voltage. Well, here's the answer. So you can see on the Keysight digital multimeter, it's right at 10 microamps, and over here, 10.00 microamps. So this is exactly in agreement, and this Keysight digital multimeter is under a factory calibration, and it's known to be very, very accurate. So I can step this down like this and go 9 microamps. It's in agreement. 8, 7, 6, 5, 4, 3, 2, all the way down to 1. No problems. And this can go down to lower values as well, but you get the idea. It is extremely accurate. Now this voltage measurement is actually the voltage that's being measured at the output terminals of the instrument, because it's not set for remote voltage sensing at this point. I don't have it configured that way. So this voltage is at the back of the instrument, and there's a little bit of resistance in the test leads, not much, but just ever so slight. And then there's some resistance through the current shunt in this digital multimeter, so the voltage drop across the test leads, and that current shunt ends up being this voltage right here. And exactly how low of a current can the Keithley 236 go down to? Well, here it is. So this is in nanoamps, so the decimal point is right there. So nanoamps, then the next 3 digits are picoamps, and the 1 is femtoamps, so hundreds of femtoamps. That's an extremely small current. All right, so the circuit board is reattached to the front panel, so now it's time to do the calibration. So I'll start with the DC calibration, and then we'll do AC calibration second. So I'll just turn this a little bit here, and you can see how everything went back together. Just touch this up a little bit on the focus there. So I just took a few pictures with my cell phone before I started the disassembly and repairs. That made for a good reference to reassemble everything. Now there's no silk screen on the circuit board, so there's no markings. So having those pictures makes a good reference to get everything back in the right location. So turned out very nice. All right, so let's set this back down here, and let's take a look at the schematic. So to do the calibration, there's two steps that we need to do for the DC calibration. And let me just get this touched up a little bit as well here. Quite so bright. There we go. So here's the meter with 50 microamps, and again we saw that 50 microamps on the meter by itself will cause it to go past the end of the dial. Okay, it goes full range, but past the last tick mark. So what we want to do is connect the Keithley 236 from this point to this point. So we're not concerned with anything else on the schematic, not even this resistor right here, only the meter and this 200K potentiometer that's in parallel with the meter. And what we're going to do is have 50 microamps, so the Keithley 236 is going to be in the constant current mode, and we're going to have 50 microamps flowing through the meter and this potentiometer, and adjust this potentiometer so that the meter indicates full scale right on the last tick mark on the meter, or on the right hand side, could say at the first tick mark on the right hand side. So again, we already saw that 50 microamps without anything else connected to the meter will make it go beyond that tick mark. So we're going to adjust this potentiometer so that we get right on that first tick mark on the right hand side. Then the second step is to connect 250 millivolts across the meter from this side all the way over to this side. So now this 5K potentiometer is in the circuit, and adjust the 5K potentiometer so that we get full scale indication, which is 250 millivolts. Okay, so this potentiometer first, this potentiometer second, and when we're doing the 250 millivolts, the Keithley 236 will be in the voltage mode, not constant current. Okay, so it'll be in constant voltage mode. So when I connect to the meter directly, I'll just be connecting right to these terminals right here. Okay, so that'll be the first part where it's in the constant current mode. And then when I need to connect for the constant voltage mode and do the second potentiometer, I'll be using the front panel jacks because we need to go across, for the complete circuit. And right now for this first procedure, first calibration, the range switch is just in the highest voltage setting over here, 500 volt, 1000 volt range. All right, so let me get things repositioned just a little bit so that you can see the Simpson 260 and the Keithley at the same time, and then we'll do the calibration. All right, so the Keithley 236 is in the constant current mode, 50 microamps, and you can see the test leads are connected to the studs on the back of the meter. And I'll be making the adjustment on this potentiometer right there, and I don't need a tool. I can just turn that with my fingers. And then the second potentiometer is this one, and I'll have to use a little screwdriver to adjust that potentiometer. All right, so get this turned back around here. You can see, make sure that is on there secure. Oh, that's okay. So with 50 microamps, you can see that the indication is beyond the last tick mark on the right-hand side. So it's indicating just a little bit too high right now. So reach around here and turn this adjustment. Yep, there it goes. You can see the needle is starting to drop down just a little bit. Right about there, maybe a little bit too far. Right there. That looks really close right there. So yeah, that's looking really good. What I'm going to do is move the camera out of the way, and then I'll be able to look straight on at the meter, and then as well lay it down like this and double check that it's reading accurately. But I think everything is looking very close at that point. So I'll just double check things off camera, and if it looks good, then I'll move on. I'll reconnect everything to the second adjustment with the 250 millivolts, and we'll adjust that potentiometer. All right, for the second DC calibration, the 250 millivolts full scale, I have the test leads connected on the front panel. So the positive is on the 50 microamp and 250 millivolt input. The negative is on the common, and the function switch is on the 50 volt and microamp setting, just to ensure that this isn't in a position that affects the measurements. And this is on the positive DC input. All right, so I want to show you what not to do first when you're doing the second DC calibration, and that's to use a constant current source. So right now this is still in the 50 microamp constant current setting, and you can see the measured voltage. Now this is indicating right on the first tick mark on the right hand side, and you'd say, well, it looks calibrated at this point, but this is what you don't want to do, and here's why. So I'm going to turn this adjustment here, so this is the second DC calibration potentiometer right here, and get this screwdriver to go in there. Okay, there it goes. So I'm going to start making the adjustment, and notice the voltage, how it's changing. And I'll go the other direction here. Notice how it's increasing. So the voltage is changing, but of course we're in constant current mode, so this doesn't change. As I'm rotating that potentiometer, we just see that the source voltage is changing, and that's changing to ensure that 50 microamps continues to flow, even though the circuit resistance is essentially changing. So that's not how you want to calibrate this. Okay, this needs to be in the constant voltage mode. And if I turn this a little bit further here, let's go all the way over, right about there. So notice this is now at 250 millivolts. So that's actually right about where it needs to be for the calibration, because now it's 250 millivolts and 50 microamps. So again, that's basically where you'd want to be, but it really needs to be done with a steady voltage, and so we need to put this into the constant voltage mode. So I'm going to just turn this back down again, put it right about there. And also keep in mind that the first calibration for the DC adjustment that I was showing you, that needs to be done only with a constant current source, not a constant voltage source. If you try and do that first calibration with a set voltage, it won't work correctly. So keep that in mind when you're doing these calibrations. So let me switch this over here to turn this off. Let's go to constant voltage. And let's double check this here. So we're on 250 millivolts. And the, let's see here, compliance is on 80 microamps just for safety. So that's fine. Okay. So obviously needs calibration because it's off the end of the range, off the end of the scale right there. So, and you can now see actually 59 microamps is flowing through the circuit, and when this is calibrated correctly, this is going to be at 50 microamps when this is dialed in and reading correctly. So let me go back over here. This adjustment here. We need to go the other way. Oop, there we go. Okay. So right there looks very close to being right on that first tick mark on the right hand side. Again, I'm going to double check this with the camera out of the way, but I'm going to say that that is really close right there. It looks like, yeah, looks good there. And check it out, 50 microamps. Perfect. That's how it's supposed to work. So again, when you're using this input, either 50 microamps or 250 millivolts will cause a full-scale indication. And this calibration is extremely critical because all of the DC measurements, and the AC measurements for that matter, rely on this calibration being correct. And the ohm meter functions as well, and the current functions, all of them, everything relies on this DC calibration being accurate. So if these first two calibrations are not correct, then the entire meter will not be accurate in any of its measurements. So again, very, very critical, and you want a source like this that's very stable and accurate on these very small values. So this looks very good. It's basically looking spot on right there, and again, I'll double check it, and also I need to check it with the meter, laying down flat like this as well, just to make sure that it's indicating, because most of the time the meter is used laying on its back or with the handle as a tilt stand. It's angled just a little bit. But All right, so it's looking like it's working correctly. Very, very happy with the results so far. And when I get the calibration touched up, just everything's looking good here, then we'll go through and double check the other ranges for the DC voltages. We'll check the ohms function and DC amp ranges as well. And then we need to do the AC calibration. All right, now that I have the DC calibration complete, let's check the Simpson 260 and make sure it's working correctly on DC volts, DC current, and the ohm meter. If all that looks good, then I'll move on to the AC voltage calibration. Now I put a little black dot of paint on both of these DC calibration potentiometers just to lock them in position, especially this potentiometer, the way it sticks up off the board could easily get bumped. And then once the AC voltage calibration is complete, I'll do the same thing, just a little dot of paint on both of those potentiometers. And you can see I installed the batteries, and those are needed for the ohm meter. So I'm just going to take the meter and put it in the case right here. Like so. We can sit on the back, and I think the batteries will stay in position because they fit pretty snug in the battery holders. So I'll grab these test leads here and put this from common, put this over here on the 250 millivolts. So as you recall in the part 1 video, when I was checking the various resistances as I stepped through the voltage ranges, the numbers were off by quite a bit, and I want to make sure that those numbers look correct now. So this meter has a 20,000 ohms per volt rating. So when you take the full scale voltage reading and you multiply it by 20,000, that's the resistance you should see on the input of the meter. So starting on 250 millivolts, 0.25 volts multiplied by 20,000 should be 5,000. So over here, let's give an extra twist on those leads and go to resistance mode. I'm going to start on low power because this is very sensitive on this first range. There. All right, so what do we have here? Looks like about 5,000 ohms. Perfect. So that's exactly what we want to see. So very, very close. It's really reading exactly right on. And in the part 1 video, when I did this test, that was way off. So it's a good start. All right, so now over here, and I'll just move this down to the 1 volt, and let's go right here. And this can actually change now to normal power rating. So this has 2 outputs, high and low power for the ohm meter function, so it's handy when you're measuring very sensitive circuits. So on the 1 volt input, 1 volt times 20,000, of course, is 20,000, and perfect, look at that, no problems there. So now move this down here to this terminal jack, and 50,000 ohms, perfect. That's what it should be. 200K, so this is in the meg ohm range now, so perfect. No problems there. So 1 meg ohm, excellent, that's what that should be. 250 volts. So that should be 5 meg ohms, very close to that value, just a touch under, but that shouldn't be any problem. Looks very good. And the 500 volt range, 10 meg ohms, perfect. That looks great. And then 1,000 volts, we just have to move this over right here. And it should be 20 meg ohms, perfect, it is. Excellent. So the resistance readings look great. I think the accuracy is going to be very good on the meter. If I go back over here, go all the way around to the resistance ranges, so 500 milliamps, perfect. No problems there, that looks reasonable. 100 milliamps, yep, 2.8 ohms, over that, perfect. 10 milliamps, yep, 25 ohms, 25.2, that looks reasonable. And 1 milliamp. Actually, we can see we have a full scale deflection on the meter right at 1 milliamp and 250 ohms, and that looks correct. Actually, if we go over here to this setting, you can see right here, this is in the 1,000 ohm, and right here it says it's about 1 milliamp that it sources, so exactly what this is reading, so it makes sense. Perfect. All right, so let's put some voltage to the meter and see how it actually measures. So what I'm going to do here is just put this back to DC volts, and I'll move this over here to this range, all the way around here like that. And I'm going to grab these test leads. So I'm going to use this power supply, the Keithley 236, and go over here. Keithley is turned off right now. So we'll just use the Keysight digital multimeter to make the comparison. We'll just measure the voltage and see that this is reading reasonably close. And turn this Keithley 236 on. And it is set for 0.25 volts right now. So what do we have? Perfect. It's right at full scale. And you can see 0.25 volts. So excellent, no problems there. Very reasonable. Just going to move this over now to 1 volt. And if I just change this here, let's go 1 volt right there. So 1 volt's full scale, perfect. No problems. So this is on the 2.5 volt range. So if I go 2.5 volts, full scale, no problems there. Looks very good. And I could back that off a little bit, like if we go back down to 1 volt. So we can see you're on 2.5 volts, so it's red on this top scale. It's 2.5, 2, 1.5, 1. It's right there, perfect. Okay, let's go to the 10 volt scale. So I'll go to 5 volts, should be halfway. Excellent, exactly in the middle. So the accuracy is looking spot on. Go to 10 volts. Perfect. Go to 50 volts. So now in 50 volt range, 50, 40, 30, 20, 10, exactly where it should be. And now let's go up to 50 volts, full scale. Perfect, no problems there. I'll go to 250 volts. So on 250, you're reading on this top scale, so you have 250, 200, 150, 100, and then 50, so that's exactly what it should be. And the Keithley 236 tops out at 110 volts, so I'll just go to 100 right there, and exactly where it should be, right on. So now let me reconnect this to a different power supply to go to a little bit higher voltage. So I'm going to turn this back off, down to 1 volt, turn that off. And I'm just going to move these test leads over here. So this is a power supply that can go up to 1,000 volts. So I'm going to just move this over here. Okay, so we're on 250 volt range, so let's go here. This power supply is around the corner on the bench. It has an adjustment knob that I have to turn. So that should be getting close there to about 200 volts. Yep. So because this has an adjustment knob, it's a multi-turn adjustment, but it's a little bit touchy to dial numbers in, but that's very close to 200. I'm going to say that's close enough right there. And yeah, right there, 200 volts. So to my eye looking at this, it's just a little bit over the 200 by maybe one, not even 1 tick mark, maybe 1 tick mark over. It's reading just slightly high, but that's within spec. I wouldn't be worried about that. That looks okay. It's very, very close. So no problems there. Let's go all the way here to 250. Back that off just a little bit there. Again, this is a little bit touchy on the knob. It's about close enough right there. Back that down just a little bit. I think that's okay. So well, that looks very good. No problems there. So 250 volts, and we're right on the full scale mark, so I don't see any issues going on there. That's fine. And keep in mind, if you are following along and you're measuring on one of these meters, like I'm doing here, you're definitely doing so at your own risk. When you get up into these higher voltages, not something to mess around with. So take care and be safe. Never come in contact with voltages that are up in hundreds of volts like this. You need to definitely use appropriate precautions and stay safe. All right. So if you are following along, you're doing so at your own risk. All right. So now let's go here and step this up to the next range. So this is 500 volts full scale. So that looks great. 250 volts, that's midpoint, and look at that, it's right on. Perfect, no problems there. Let's go all the way up to 500 volts. So getting there, let's see, 400. There's 500, oops, a little bit too far. There, that looks pretty close. Perfect. Right on full scale. So the accuracy of the meter looks excellent. I'm really happy with the results. So now I need to turn the voltage all the way down to 0. I'm not going to be touching those test leads with that kind of voltage. Right. So it takes a little bit of time to bleed off. So I'm using the, let's see, this is that the Bertan 205A-01R. It's a high voltage power supply, and I did a repair video on that power supply. So if you're interested, check out the other video. I show inside that power supply and the repairs that I did when I first received it. All right, so now let's move this over here to the higher voltage position. So this is 1000 volts full scale. My test leads here are not quite long enough here. I need to move the meter over just a little bit like so. Okay, so we're on 1000 volts. There we go. So I'll take this up to 500 volts again. Close enough, no problems there. Let's see how this looks. Great. It's right on midpoint, halfway. So the accuracy is spot on. So let's take it all the way up to 1000 volts. So I would say that is close enough to 1000 volts and perfect, right at full scale. So all the ranges are working exactly the way they should. So let me reconnect things a little bit here in a different way so that we can measure the DC current ranges. Start by lowering this voltage down. Multi-turn potentiometer there. You might be able to hear that as I'm turning it. There's a counter that has digits on it that looks like an old-fashioned speedometer where the numbers go by, and it's a little bit noisy when you turn it quickly there. All right, so that bleed off a little bit. So I'm going to connect this back over to the Keithley 236, and I'll use that as the current source, and let's check these current ranges. And then I'll have to reconnect things differently with an electronic load, and we'll check this 10 amp shunt. But I'll do that after we measure the lower ranges first. All right, so that's let off there. So disconnect this. Okay, so what we need to do here is make a couple changes on this. I'm going to unplug that for a second. So I think we can go like this. Start 500 milliamps. I'm going to set this to DC current. All right, so I have the Keithley 236 connected coming in here on this current input, which is a 3 amp jack, and this will auto range accordingly. And then coming out here on the common terminal jack, comes over here to the input on this positive, comes out of the common and returns back over here on this other test lead, which is going over to the Keithley 236. So essentially these two meters are in the current measuring mode. They're just in series with each other, so we can compare the readings we get here with the readings on the Keysight. All right, so this is on 500 milliamps. Start here with, this can only go up to 100 milliamps. So let's go right here. Let's see, we need to enter, operate. Okay, that is not where we want to be. It needs to be, there it goes. Perfect. Okay, so 100 milliamps. So 100 milliamps there, and looks good. So 500 milliamps full scale, and we're reading this second range numbers down, and perfect. It's right on the tick mark. So no problems there. So if I go to 100 milliamps, this should go all the way over. It is in compliance mode. We need to change this here. Let's let that go a little bit higher. That should be fine. It was hitting the compliance voltage level on the Keithley 236. All right, so there's 100 milliamps. And perfect, full scale. So spot on, no problems. Let's go to 5 milliamps. So here. Okay, there's 5 milliamps. And let's go here to the next range. So it should be halfway. Perfect, no problems. Try 10 milliamps. Excellent. And let me drop this down to 1 milliamp. So there's 1 milliamp, and we'll go like that. Perfect. How cool is that? Very accurate. There's 500 microamps, or half milliamp. Perfect. And we've already seen that this 50 microamp input is working correctly, because if it works on 250 millivolt input, it will also work on 50 microamps, and we saw that during the calibration. So the current ranges and the voltage ranges are spot on. So now let's take a look at the resistance ranges. So I'm going to turn the Keithley back off, standby mode. And what I need to do is change this around just a little bit here. Pardon all of the test lead rearranging. Just kind of change this around here. So of course, for a resistance reading, both meters cannot be connected to the same resistor, so one at a time. So I just have a couple sample resistors, and we'll compare the reading on the Keysight and what we get over here. And on this over here, what I need to do, back to mode there, like so. All right, let me grab a resistor here. I think this is an 8 ohm resistor. Yeah, this is an 8 ohm power resistor right there. So just connect that right here, and let's see what we actually get here on the measurement. Okay, so yeah, very close to 8 ohms, no problems with that. So now, first thing we need to do is zero out the reading here, so the test leads are just connected together. Perfect. So we're reading ohms, which is on this top scale. So there's 5 ohms, and then here's 10 ohms. So 5, 6, 7, looks like that would be 8. So it's reading just a little bit under. That'd be 9 and 10, so 8, 7. It's reading about ohm off. It's just a little bit off right there. Not quite on 8 ohms. Double check this. Check that again. 10. Yeah, it's reading just ever so slightly low. But not too far off. Let me try the resistor right here. Here's a 100 ohm resistor there. Let's see how we do. So 103 ohms. Let's try that. So on the far end of the scale here, there's 100 ohms. It's very close to the 100 tick mark. Perhaps just ever so slightly above it right there, but very, very close. And if I have, let's see here. Here's a 300 ohm resistor. Let's try next range right here. Let's try this one. So about 313 ohms. So this is on the next range. Let's try that. So that looks very good right there. So again, we're on this top scale and it's times 100, so that's 200, and then 300, 400, and 500. So that's very accurate. That looks good. No problems with that. So that first resistance range, perhaps just ever so slightly off, but it's not far. You know, it is very close. And let's try the highest resistance range right here. With this resistor, I think this one will work. Let's try this. I think it's 150 k ohm. Yep, it is 150 k ohm. This is zeroed. That. Perfect, look at that. 150 k ohms, right on. So overall, not too bad. Looks pretty good. And going back to a voltage measurement, if I go over here, let's go to 10 volts. But I'll put this on the minus DC. I hadn't tried that range yet, just to make sure the switching is working correctly. So I'll just disconnect these leads right here. And I have 10 volts set on the Keithley 236. Let's just plug that in here. But now we're going to reverse this. So negative that, common is positive, and yes, perfect. So you reverse the polarity, but this is on minus DC, and it works correctly. So perfect. Let's move on to the AC voltage calibration. So I almost forgot about checking the 10 amp range on the Simpson 260 before I move on to calibrating its AC voltage ranges. So let's check that high current range now. So I have a large DC power supply connected to this electronic load. You can probably hear that fan running in the background. That's that big Sorensen SRL 40-25. So it's a 0 to 40 volt up to 25 amp capability. So I have it set to 10 volts, and you can see that's being displayed on the electronic load. So I'll step the electronic load all the way up to 10 amps, and we'll watch for the indication on the Simpson 260. So the 260 is just connected in series between this electronic load and the power supply. All right, and you can see the test leads are up here on the high current range jacks, so plus 10 amp and minus 10 amp right there. And then this is over on the 10 milliamp and amp setting right there. Okay, so here we go. Let's take a look here. Go 1 amp, enter, turn that on. So perfect. It's right on the 1 amp tick mark right there. So just step this up. 2 amps, looks good. 3 amps, looks good. 4 amps, perfect. 5 amps should be mid-scale, spot on, looks very good there. 6 amps, yeah, very good. 7, Settles right in there, no problems. 8. Perfect, spot on. 9. And 10, full scale. Excellent. Perfect, it's very accurate on the high current range, so I'm happy to see that. So that large shunt that's inside the meter that I already pointed out is very accurate, and we already looked at its resistance readings a little bit earlier in the video, and the resistance on that shunt looked correct, and obviously it is working the way that it's supposed to. All right, let's move on to the AC voltage calibration. All right, let's finish up with the AC voltage range calibrations. So there's 2 calibrations that have to be done. One's at 250 volts AC, and the other is at 2.5 volts AC. So you do 250 volts first and the 2.5 volts second. Now there is some minor interaction between the 2 calibrations, so after you do the calibration once, you probably should go back and check it a second or maybe even a third time. Just continue until no further adjustment is necessary. I'll go through the calibration once on camera, and then any further touch-ups I'll just do off camera. All right, so taking a look at this drawing right here, you can see this potentiometer is R22, and that's used for the 250 volt adjustment, and R25 is used for the 2.5 volt adjustment. Now for the 250 volts AC, I'm going to use my Agilent 6812B AC source. And I featured that in a repair video a while back, so if you're interested in seeing that, definitely check out that other video. Now the reason I'm using that AC source is because it provides an isolated output, which is important for safety. The same idea as using an isolation transformer. Of course, if you come across both AC lines at the same time, definitely a shock hazard, but it is isolated from ground. And also it provides a very clean and stable and regulated output, so it'll be a very stable AC voltage. If I use my isolation transformer and the variac to set the voltage, you know, there's line voltage fluctuations in the shop when devices are turning on and off, so it's nice to have that very stable output when you're doing a calibration like this. And that fan noise that you hear in the background is that Agilent 6812B that's running. The fan's a little bit on the loud side. It's a pretty big cooling fan in that instrument. Now for the 2.5 volts AC, I'm going to use my function generator. It's a BK Precision 4062B, and that provides a very accurate and stable output, and it will work very, very well for the 2.5 volts AC. So I have it on the sine wave output. And the AC source can go down to 2.5 volts, but the function generator is even more accurate. So I'll go ahead and just use that for that low voltage range. Okay, so everything is connected right now. I do just want to show you one other thing here on the back. I took the batteries out of the meter because they make it top heavy, and the last thing I want this to do is topple over when I'm trying to work on it. And if you are working on a meter like this and following along, you're definitely doing so at your own risk, especially with these higher AC voltages. Definitely a shock hazard, and you wouldn't want to put your hand around here and come in contact with something on the back of the instrument. You know, down in here you've got terminals down in here that are going to have live AC voltage on them. Don't forget the fuse holder has AC voltage on it, so definitely shock hazards on the back of the meter, and of course necessarily it's apart when you're doing this calibration. And I'm going to use an insulated screwdriver right here to make the adjustments. Alright, so this is on 250 volts, and I have the Keysight digital multimeter just in parallel so we can monitor the voltage over here as well. It's just connected across the line. Okay, so let me reach around on the other side. The AC source is over here on this other shelf, and turn this on. There we go, 250 volts. And of course 60 hertz. Okay, so we can see 250 volts. And this is indicating less than 250, so it should be full scale. Now, don't forget on AC voltage, you're reading these red scales down here. So there's 2 red scales, and for all the voltage ranges except 2.5 volts, you read the upper red scale. The numbers are in black, of course, right there, but you're reading the tick marks on that red scale. And then on 2.5 volts AC, you're reading this lower scale, which is basically shifted off just a little bit in relation to the other scale. So make sure you're looking at the correct scale when you're taking those AC voltage measurements. Okay, so let me go over here and reach around very carefully here. So we want R22. It's all the way here on this edge. There it goes. Okay, it's increasing. So that looks like it's right at that tick mark there. I'm going to turn this a little bit so I can see it. That looks really good. When I look straight onto the meter, it's right on the last tick mark on that red scale, so I think that's looking very good at this point. So we'll call that set for now. So let me go over here. I'm going to turn off the source. All right, so that's turned off. Now I'm going to move these test leads over. Okay, so there we go. So there's 2.5 volts. It's right there. All right, so 2.5 volts. And both potentiometers were just at the midpoint of the range for starting. So now we'll go to this next one, and let's make sure that's there. That's good. Oops, make sure we have a good connection that dropped down just a little. Let's make sure that's, we go 2.5, that's fine, okay. So R25 right here. Touchy right there. Let's get that just a little bit more. Oops, that just went a little too far. There we go. Okay, so that's right on the last tick mark on the 2.5 volt range right there on the AC scale. So call that good for now. So again, I'll go back through and double check this, and also I want to check with the meter laying on its back as well, just to make sure it's accurate. So I'll do that off camera. So let's check the other ranges now. So 2.5 volts looks fine there. Go to 10 volts. And let me just move this back over here to the AC source. And I'm going to go around the corner here to this, go voltage, and let's go to 5 volts. Start with, turn that on. So essentially 5 volts, how does that look? Very good. So of course 5 volts is going to be right in the mid scale right there, and it's right at the tick mark. Perfect. Let's take a look at full scale. Go here, let's see, voltage, 10 volts. Excellent, no problems. Full scale reading looks good. Go to 50 volts, so now that is, yes, that's perfect. Right on that tick mark. So that's 10, on the 50 volt scale, that's the 10 volt reading. So let's go all the way up there to 50. All right, perfect. Full scale, no problems. 250 volts. And yep, very good. It's right at the tick mark there. Looks good. Let's increase that. So we already saw the 250 before. It looks like it's still remaining very accurate. It looks like that really hasn't changed at all, so that looks fine. Go to the 500, so that should be mid-scale. Yes, it is. Perfect. So looking very accurate. Now, the highest voltage I can go on this AC source is 300 volts, so we'll go voltage 300. We'll bump up just a little bit more, and perfect. Yep, that's right on 300. Looks fine. Let's see, 500, 300 would be, it's just, I would say it's just ever so slightly high beyond that tick mark, just a little bit, but it's very, very close. So I'm not worried about that. That's looking okay. Now let me turn this off, and I'll go to that other highest voltage range, turn that off. Move that over there. So the 1000 volt range. Turn this back on. Still 300 volts. And how does that look? That's 1000, 64300. Yes, that's spot on. Perfect. Right there, that's right on the tick mark. So excellent. Accuracy is looking very, very good. I'll double check the AC calibrations here a second time on the 250 volts and the 2.5 volts, and then I'll put the meter back together. So I hope you enjoyed following along on the repairs and calibration of the Simpson 260 Series 6 Volt-Ohm-Milliammeter. The meter is working very well at this point. I'm definitely looking forward to using it on the bench for troubleshooting. You'll probably see it featured in some future videos. So if you did enjoy this video, you can let me know by giving it a thumbs up, and don't forget to share the video as well. And if you're enjoying the videos on this channel, please remember to subscribe. There'll be many more videos coming up in the near future. Lots and lots of projects in the queue. You won't want to miss any of those. And thank you to all the viewers who have taken the time to subscribe. Definitely means a lot, and it helps the channel to grow. All right, as always, thanks for watching, and until next time, take care. Goodbye for now.